Hi, this second section for limits, we're gonna learn how to actually observe limits from a graphic point of view. So first, let's define what a limit is. So if you suppose that you have a function that is defined for all x near a point A, except maybe that point A, and if f of x, so the image of the function, is arbitrarily close to a certain number L, or as close as we like, then for all sufficiently close but not equal to A, we say that the limit when x goes to A of f of x is L. Okay? And say that the limit of f of x as x approaches A is equals to L. So just to show that better, let's consider this function here. So imagine that we're gonna step in certain points. So for example, let's step in x equals 2. So if you see x equals 2 has a very different very different value for the function that what the function is approaching. The actual value of f is 5. F of 2 in here is going to be 5. However, if you ask when you take numbers that are getting closer to where are we going, is a very different value. Notice if we take values for between 1 and 2, so we approach 2 by the left, when you check the image, you're gonna see that those numbers are approaching 3. You move by the right side as well, you can see that those numbers in the function are approaching 3. So in this scenario, it happens that the limit when x goes to 2 of f of x is 3, although the function f of 2, the function in 2 is 5. And it turns out that the limit might exist without I even having to have a value for the function. So in this case, as an example, f3 is not defined, but when you approach by the right side and by the left side, you can see that the function is going towards the value of 4. So it's like almost you have something in here, but you don't. And so the value of the limit in here is 4. Okay? So just to comment a little bit more in this, notice that every time that I'm talking about approaching x, I have to look over here below. And so I'm in the x-axis and I'm approaching by the left or by the right side. So in here I'm approaching x to 1, and I approach by the left side or the right side, and I need to see where the value of y is approaching both and for both sides. So for example here, when x approaches 1 by the left side, this is approaching 2. The function, the height is approaching 2, and here by the right side, the function is also approaching 2. Okay. Notice that if we step in 2, as I mentioned before, then we're just getting closer and closer to 3, even though the value of the function is different and is 5. And similarly, if I approach 3, then the values of the function are going to approach 4, because that's the height that we have. And so limit is something that is very different from just the definition of the function. As you can see, the function values might exist or might be different from what the limit is. Now, we can also sometimes see where a limit is going just by checking the values nearby with a table. So for example, here we're going to take the function f of x equals the square root of x minus 1 divided x minus 1, and what we're going to do is we want to know the limit when x goes to 1. So what we do is we plug values. So for example, we're going to plug 0.9, and when I plug that in this function, I'm going to get this value, 0.131670. When I get closer, so I do 0.99, now this becomes f of 0.99 becomes 0.501. And if I get closer more, 0.99, notice that that's become 0.50. And if I get really close to 1 by 0.9099, that's 0.50 and some decimals. So I can say that this limit by the right side, by the left side is approaching 1/2 or 0.5. Now if I go and look to 1 by the right side, I'm going to have a similar behavior. I start closer from 1.1, and that's 0.48. And 1.01, it becomes 0.49. And in 1.001, it becomes 0.49. So very close to 0.5. And then from this, we can conclude that indeed this limit is going to be 0.5 when we approach 1 by left side or by right side. But now, if I'm talking about approaching by the left or by the right side, is probably worth making a definition in terms of limits in the sides, lateral limits. And so let's do that. The definition for this is called one-sided limits. And so the right-sided limits is suppose that you have a point A that you want to approach, and you want to get arbitrarily close to a number L. And so when that happens, what we're saying is that the limit is L if every time that I increase my approach by the right side, I'm getting to that point. So let me explain. So assume you have point and your number is A, and here we have the y bar, and it turns out that you're getting this function, and this height is L, and let's do this one here, and this height here is R. So in this in this particular function, we can say, oh, okay, so we're getting closer to A. On the right side, the numbers are getting closer to L, to this height. So in this, we can say limit when x goes to A by the right side of the function is L. Probably you can guess by now that if we do the same thing by the left side, so we're taking points here, then we're getting closer and closer to this number R in there. And so this is limit when x goes to A of this is R. Okay. And so this is the idea of the one-sided limits. And when I can say that both by the left side and by the right side I'm approaching the same number, then I can say that the general limit when x goes to A is L. Now, let's see one example. So consider the function x cubed minus 8 divided 4x minus 2. So this is a computer generated graph, and it's a little bit inaccurate because this function is not actually defined at x equals 2. So actually the function is going to look a little bit more like this on the right side. It's going to have a hole in here. And so what that hole means is that we don't have a definition for when x is equals 2. Remember, that's a problem in the domain. You probably saw that in pre-calculus. And so at this point, this 2 is not defined in there. It doesn't look, apparently from the graph, that this is going to be an asymptote. So in this case, what most likely happens is that we're going to get that the limit is going to be 3. Of course, you can see that when you approach by the left or the right side. Notice if you approach by the right side, when x is over here, the value is here, which is quickly approaching 3. And when you're going by the left side, the similar thing is happening. You're getting very close to the point 3. And so at this point, we can say that the limit when x goes to 2 is going to be 3. Okay? And by the way, the notation of that, will be limit when x goes to 2. And so this will be the right, and we're using the function right. We're using x cubed minus 8 over 4x minus 2, and this is gonna quickly approach to 3, and we can see that the same thing is happening by the left side, so we can write this. And so the implication that in both cases this is going on implies that the general limit when x goes to 2 is 3. If these are different numbers, by some reason, this is not going to happen. Okay? All right. And so graphically, we can see, again, the limit is a quantity that is in y. F of x is a quantity in y, and the limit is also a quantity in y. Now, a similar thing can be seen again if we do this with a table. Notice that using the calculator and plugging values nearby is going to produce a similar type of behavior. This is going to show you that if I go by the left side, the numbers on f of x are going to approach 3, and if I take numbers on the right side, then this is going to approach 3. Okay? And so as I was mentioning, which we'll state it now as a theorem, the relationship between the one-sided and the two-sided limit is that for the limit to assist a certain point, it's necessary that the limits on the sides assist and are the same thing. Okay, and this is an if and only if condition. So if the limit assists, then it's because in each of the sides the limit is L, and if in both sides the limit assists and is L, then it's because the general limit is going to assist. Okay, so now let's take a quick look here. One example where that's not going to happen. Notice that this for this function g of x, when x goes to 1, in particular, when x goes to 1, by the left side, the limit goes to 2, clearly the function is approaching 2. And if I go by the right side, then the function is approaching minus 2. So these limits are going to be different, and hence the general limit when x goes to 2 is not going to assist. Okay? Now another example of this will be checking the function cosine of 1 over x, and sometimes it gets very difficult to see if this is going to happen. So for example, the values of cosine of 1 over x, they're always oscillating between -1 and 1, but the closer that we get to 0, the faster the oscillation is. Notice that this becomes really large. 1 over something getting closer to 0 is like 1 over something really small, which is gonna in turn transform to something close to infinity. So that's why this graph looks like this. If we can see it really from the function or from the graph, the best scenario that we can take is make a table. And so notice what is going to happen from the table. So if I initially start with closer like 0.01, I start getting 0.56. When 0.01, it produces minus 0.95, and then if I get closer, it produces 0.99. So if we only leave these numbers, we could incorrectly assume that this is approaching -1 when we're approaching from the right. But it turns out that that's not true. If we move a little bit more, notice that 0.0001 produces 0.93. We lose the negative number. And then if we move again, then it jumps and is negative again. So in this case, what's going to happen is that this limit is not going to exist because we cannot approach a single value. Remember that for the limit to exist, we need to approach a value. Well, in this case, we're not approaching any value, and therefore the limit is not going to exist. Okay? And so this is the introduction to how to calculate limits. This is the theory behind the main ideas. Next video is going to show a little bit more on how to do this calculation and how to observe this more in the graphs.